This video will be about centripetal force. For any mass that's moving around with centripetal motion, it should experience centripetal force. So as a brief reminder, there's more notes available on the class website. I've got a slightly different version of notes that are posted on March 19th. That's mainly what I'm going through today. There are other websites that have a lot more thorough information. This is a good site right here. Goes over your apparent weight and how you'd feel heavier or lighter depending on where you are on a roller coaster that is undergoing some uniform circular motion. You can read through that. I'll just go through some basics. So when you're moving around in a circle, you have constant speed and you should have centripetal acceleration causing you to turn around in a corner, and it should always be directed towards the center of a circle. Regardless of where you are in your turn, you should experience centripetal acceleration always towards the center of the circle. And since we're working with forces, anytime there's an acceleration, you typically have some kind of unbalanced force. So in this case, it's no different. Your centripetal acceleration is providing you that centripetal force. Sometimes people call it centrifugal force. That is a made-up force, doesn't actually exist. If anything, that's inertia. So that's that force that some people say is there because if you turn left really sharp in your car, your body feels like it wants to go to the right. That's just inertia. You were already going pretty much to the right. Well, you're going straight, but it's going to feel like you wanted to go to the right when you crank on your steering wheel hard to the left. That's just inertia. So centrifugal forces don't exist. This is centripetal force. So the centripetal force is going to go in the same direction as your centripetal acceleration. And it's no different than the force questions you've done before, where your net force acting on a mass should be equal to the sum of all forces. But in this case, since it would be going around in a circle, our mass times acceleration gets altered to mass times centripetal acceleration. That there is your centripetal force. Your net force becomes your centripetal force. I dropped the vector symbols because for the most part, the direction is continuously changing. So we just call it pointed towards the center of the circle or the curve. So if I combine that with the last lesson, knowing that we had two different equations to calculate your centripetal acceleration, we can change your net force or your centripetal force into your mass times your speed square over your radius. And if you remember, your speed for centripetal motion should be 2 pi times the radius, all divided by the period. Then if you substitute that in there for your speed, you end up with a net force equation that is related to the radius of the circle or curve divided by the period square. So some things that people tend to forget: if you're moving in a circle, your net force is your centripetal force. So this center F here is often just ignored, and we typically just deal with that through centripetal acceleration. So I've got two questions I'll try to go through with you guys real quick. Question one: if you have a car and enters a level curve at 20 meters per second, the curve has a rough radius of 80 meters. What centripetal force must be supplied by friction to keep the car from skidding? So our tires rely on friction to stay on the road. And if you're going to maintain your speed as you go around a corner, you're going to want friction to keep you on the road. So there's your car. Not an artist, that's your car. So suppose it's driving forward. Maybe it's you're on the highway, you're going forward, and there's a curve up ahead. You would probably just not think about it. You drive forward, you go around the curve, and you come out of the curve. But that curve would technically be part of a larger circle if you work it out. So that has a radius R, so 80 meters, 20 meters per second. You're looking somewhere around 80 kilometers an hour. Somewhere around there. Friction is keeping you on the road. So as you're car wants to continue to go straight, if you turn the wheel along with the curve of the road, the friction will keep your tires on the road, but that means you are going to accelerate towards the center of the circle. If you're using the diagram I have on the screen here in front of you, that just means you're going to be wanting to turn from rightward motion to downward motion. So your friction should be the only force acting on it, and therefore that's going to be equal to your centripetal force. So your centripetal force goes towards the center of the circle. Your centripetal force, since we were given speed and radius, I'll just use the equation for centripetal force, mass times speed squared divided by radius. And then it just becomes a plug and play question. You substitute in the 1,000 kilograms for the car, the 20 meters per second for your speed, square it, you get 400, and then you divide it by 80 meters. So in this case, your friction should give you about 5,000 newtons. And just off to the side here, on the left-hand side, I just wrote down the units, kilograms, if you square a meter per second, you'll get a meter square per second square, just to show you how the units cancel out. And it leaves you with a kilogram meter per second square, and therefore a Newton. So the other question I'll put on this video is a question that physics teachers, physics professors, and just in general, anyone who's played around with a Hot Wheels car usually loves the gravity-defying loop-to-loop. They've done this, and by they, quick little search on YouTube, real cars have done the loop-to-loop. I think it was a stunt, a YouTube stunt put on by Hot Wheels, and I forget which car company. Won't take you too long to YouTube it yourself. So you can do a loop-to-loop in real life, but you guys probably experience this either with a roller coaster or just your Hot Wheels car. So as this car is going around this vertical loop-to-loop, I didn't make the animation. There's only one thing that's kind of wrong with it, the fact that this little yellow arrow changes in length, so it's really small at the beginning, but then suddenly gets really big. Just try to ignore that part of it. Just focus on the fact that while it's going around the loop, the arrow decreases as it's going up, and it increases as it goes down. So that is the normal force. And if this car is going at the slowest possible speed where it's still able to make this vertical loop at the very, very highest point, right where the mouse is or right at the very top, that yellow arrow disappears. There is zero normal force acting on the car at that exact moment in time. Right, slightly beforehand, there's a small normal force. Slightly afterwards, there's a small normal force. But right at that very apex of the circle, of the loop, there's zero normal force acting on the car. It's hovering, if you will. So at that point, there is only one force acting on the car, and that is the car's weight. So that's represented by the small little red arrow underneath the car. So as the car is going around the loop-to-loop, it would have a net force, and since it's going in a circle, that force would have to be equal to your centripetal force. Now, its speed is changing, it's going around here, so we're assuming that we're looking for the slowest possible speed, and if the car maintained that slow speed as it went all the way around, and that speed was uniform, then this equation will more or less work out the basics. So your free body diagram says at the very, very top, at this point right here, your net force, sorry, your free body diagram only have your weight, so that's what the free body diagram would look like. So only your weight is pulling it down, and since your net force is the sum of all forces, well, you're stuck with this. So therefore, your net force is equal to your weight. Plug it into the equation on the right-hand side there. Your weight is therefore equal to your centripetal force. Your weight, of course, is your mass times your acceleration of gravity or your gravitational field. Your centripetal force, since we were given the radius and we were looking for that minimum speed, I'll use the centripetal force equation, mass times your speed squared divided by your radius. So as you can see, I've got mass times gravity is equal to mass times speed squared over radius. I have mass on both sides of the equation, so we can just cross those out. get rid of them all together. From there, you just do a quick manipulation. You bring your radius to the left-hand side of the equals. I usually prefer mine to have the work I'm going to deal with on the right-hand side, so I'll just flip my equation around. So to get rid of the square, you just take the square root and then just plug in your numbers. So acceleration and gravity, 9.81, there's my chicken scratch, 9.81 meters per second square times the 20 meters of the radius of the circle. And just plug and play. You should get about 14 meters per second, which is about 50 kilometers an hour, give or take. And yeah, so that's just a couple examples of questions you can go through. There's more notes online to read, but that's the basics.